Hey, so it's Mr. Shrum, and I'm back to finish up this magnets and their fields tutorial. We left off right before we started the illustrating a magnetic field portion. So let's get into that. Illustrating a magnetic field. Magnetic fields are force fields that exert magnetic forces on substances sensitive to magnetism, such as iron and nickel. The image shows a mapping of the magnetic field lines for a bar magnet. This image is called a magnetograph and can be created by sprinkling iron filings on a magnet resting on a white piece of paper. Note that the iron filings align with the lines of the magnetic force produced by the bar magnet. The magnetic lines of force indicate the presence of the magnetic field. The line pattern begins at the North Pole, travels to the South Pole, and then re-enters the magnet. The circular looped pattern continues with the greatest concentration of force being at the poles of the magnet. Note that the magnetic force is present in 3 dimensions, but we can only see the image in 2. Now let's look at the pattern of the magnetic field when we add another magnet. In the image, we see that these 2 magnets are placed together with like poles facing each other. And if you remember, like poles repel each other. Iron filings have been sprinkled over the 2 magnets, and you see the filings are concentrated at the poles. They spread out as they move toward the center of the magnet. The area where the filings are not gathered is between the magnets, which indicates that the magnetic fields are repelling each other. So when the same poles, either north-north or south-south, are placed near each other, repulsion occurs between the magnetic fields. The magnetic forces of the 2 fields are pushing them apart. The expression likes repel come from this phenomenon. The expression likes repel. I don't know how many times that expression is used, but okay. Now, how is the magnetograph in this image produced? Here, 2 magnets are again placed together, but this time with opposite poles near each other, so north and south poles. We sprinkle those iron filings over the 2 magnets again, and then note the patterns that form. Similar to the other images, the filings concentrate at the poles of the magnets and then spread out as they move towards the middle of the magnets. This time, something different happens between the magnets. Magnetic field lines in a flowing loop form. This pattern indicates that the 2 magnetic fields of the magnets are attracted to each other. Their magnetic forces are pulling them together. So when opposite poles are placed near each other, attraction occurs between the magnetic fields. This magnetic phenomenon led to the expression opposites attract. I think that one's much more common. Now we're going to examine a few magnetographs on your own and then describe your observations. Remember, the magnetic forces between opposite poles will be attracted to each other. Similar poles repel each other. So we're going to open up. We're just going to be given pictures, I think. Explain the magnetograph below, describing the pattern of the magnetic field lines. We observe a bar magnet with iron filings aligned around it. The magnetic field induces magnetism in each of the filings, which then line up in the field. The field lines are continuous and the interactions between the filings produce loops. You see the loops. Cool. Now we have 2 magnets facing each other. Why do they align this way, and what does this tell you about the arrangements of the magnets? It looks like this is a like pole interaction, either north-north or south-south poles facing each other, and the iron filings are separating. They are repelling each other. In this last magnetograph, what do you observe about the pattern of the iron filings? Why do they align as they do? What does this indicate about the arrangement of the magnets? Well, this is a opposite pole, so north-south or south-north, and the filings are attracted to each other, or the poles are attracted to each other. And the iron filings are lining up like that. Cool. In the simulation, you predicted the direction of the magnetic field for different locations around a bar magnet. You can also examine similar magnetic fields around an electromagnet. And you can build this from a simple wire and battery. Remember, current running through a wire causes a magnetic field. One of Nikola Tesla's most famous inventions was the Tesla Coil, closely related to a simple electromagnet. His idea was to have this coil transmit electrical power without the use of wires. He hoped to use Earth's magnetic field along with a power source to conduct electricity. This strategy proved unsuccessful, but the attempt led to the creation of the radio transmitter. This invention propelled the concept of electromagnetic forces, which is one of the four fundamental field forces of nature. Electromagnetism allows current to flow through wires and coils and is responsible for practically all the phenomena in our modern world of technology. It is also the basic force behind electromagnetic radiation, including light, X-rays, microwaves, and radio waves. Match each description with its correct magnetograph. Drag the items on the left to the correct location on the right. This is a single bar magnet. Magnetic lines travel through the magnet from south to north. Yes. Okay, so this one looks like poles together. So it's either south-south or north-north. And they would repulse each other. And that leaves this one to be north-south. Opposites attract. And there you go. So, in summary, Nikola Tesla was born on July 10th, 1856. On the night he was born, there was a terrible electrical storm. Was it fate that he turned out to be known as the father of modern electricity? Tesla thought that electric power use in his time was inefficient, and he set out to improve it. As a result, he discovered a new pathway for electrical power, AC, or alternating current. From there, a new era was born. Tesla studied both engineering and physics, but he is best known as the most prolific inventor in history. He made revolutionary contributions to the fields of electricity and magnetism in both the 19th and 20th centuries. Thanks to his many discoveries, today we have technologies such as radios and wireless communication. In recognition of Tesla's numerous accomplishments, a large portrait of him is displayed in the Statue of Liberty Museum, And in many states, July 10th, his birthday is celebrated as Nikola Tesla Day. So, in this lesson, we studied magnetism, the result of the movement of electrical charges through a material. The magnetic forces in metals such as iron, cobalt, and nickel are easily detected. We saw this in our discussion of the magnetic field lines created by sprinkling iron filings around a magnet. We learned that the ends of a magnet are called the magnetic poles, north and south. When two magnets come in contact with each other, the rule of attraction and repulsion is simple. Like poles repel each other, while opposite poles attract each other. Magnets can be either permanent or temporary. Once something is magnetized, a permanent magnet will remain that way. A temporary magnet, though, can become demagnetized. It needs a magnetic source to remain magnetic. When two magnets are near each other, we see attraction or repulsion. If the arrangement is north-south, the fields are attracted to each other. When they are placed in a north-north or south-south orientation, the fields repel each other. And that's that. So I will see you all next time for our next magnetic lesson. But until then, have a great one, and I will see you all later. Bye-bye.